Good afternoon, ladies and gentlemen. Can you hear me? How are you guys doing? I am glad you guys are also doing well. So, this is our second last lecture for this module. Can you guys believe it? So, before we start, I thought of showing you guys three videos of what we will be talking about today. And hopefully, it will give you a different perspective on meteoroids, asteroids, and comets.
Diagram of the solar system, you'll see a big gap between Mars and Jupiter. A few centuries ago, that gap bugged astronomers. They really wanted there to be a planet in there. On the first day of the 19th century, January 1st, 1801, they got their wish. Kinda? Italian astronomer Giuseppe Piazzi found a point of light moving at just the right speed to be the desired planet. But it was just a dot, and too faint to physically be a terribly big object. He suspected it might be a comet, but follow-up observations showed it wasn't fuzzy. The object was given the name Ceres, but was it really a planet? Well, one diaphragm for mankind. Hopes were high that Ceres was the wished-for planet between Mars and Jupiter. But then something rather amazing happened. A little over a year later, in 1802, another one was found. Then in 1804, astronomers spotted a third one, and a fourth in 1807. It was becoming clear that a new class of solar system object had been discovered. Given that they were all just dots in the telescopes of the time, points of light like stars, they were given the name asteroids, which literally means star-like. By the end of the 19th century, more than 450 had been found in total. The rate of discovery has accelerated over the years, and now, today, we know of hundreds of thousands. There are probably billions, yes, billions of them larger than 100 meters across in the solar system, and over a million larger than 1 kilometer in size. So what are we dealing with here? What are these asteroids? There's not really a hard and fast definition of what's an asteroid and what isn't. But generally speaking, it's a class of smaller bodies that are rocky or metallic that orbit the sun out to Jupiter. Objects past Jupiter have special designations that we'll get to in the next episode. Over the centuries, we've learned a lot about them by scrutinizing them with telescopes. Asteroids come in a few basic flavors. Most of them, about 3/4, are carbonaceous, which means they have lots of carbon in them. About a sixth are silicaceous, heavy on the silicon-based materials, rock. The rest are lumped into one catch-all category, but are dominated by metallic objects, literally loaded with iron, nickel, and other metals. So many of them orbit the sun between Mars and Jupiter that this region is now called the main belt. The main belt has structure. For example, there are very few asteroids about 425 million kilometers from the sun. An asteroid at that distance would have an orbital period of about 4 years, a simple fraction of Jupiter's 12-year period. Any asteroid there would feel a repeated tug from Jupiter's mighty gravity, pulling it out of that orbit. The resulting gap is called the Kirkwood gap, and there are several such asteroid deserts, all with simple multiples of Jupiter's period. In this way, the main belt is like Saturn's rings, whose gaps are carved out by the gravity of the orbiting moons. Another way to group asteroids is by orbit. Some have similar orbits and may have formed from a bigger parent asteroid that got disrupted by an impact. These groups are called families, and there are a few dozen known. For example, the Eunomia family has over 400 members and are silicaceous, rocky asteroids. and probably all formed from a parent body that was about 300 kilometers across. When you watch movies, they always show spaceships dodging and swooping through asteroid belts, trying to evade the bad guys. But in reality, our asteroid belt is mostly empty space. On average, decent-sized asteroids are millions of kilometers apart, so far that if you stood on an asteroid, odds are good you wouldn't even be able to see another one with your naked eye. And despite their huge numbers, they don't add up to much. If you took all the asteroids on the main belt and lumped them together, they'd be far smaller than our own moon. Ceres is the biggest, at about 900 kilometers across. It's round, nearly spherical due to its own gravity crushing it into a ball. A funny thing about Ceres, as we write and record this episode, it's being visited for the first time by a spacecraft named Dawn. That means everything I tell you about this asteroid is probably about to be obsolete. But we do know a few things. Ceres probably has a rocky core surrounded by a water ice mantle. The amount of water in it is staggering, probably more than all the fresh water on Earth. It may even be liquid under the surface, like the oceans of Enceladus and Europa. Early images by Dawn as it approached the asteroid show its surface is heavily cratered, and some craters are very bright. They may be exposing ice under the surface, or just fresher, brighter material. There are tantalizing observations of localized water vapor on the surface, which may be from sublimation, ice turning directly into a gas due to the sun's heat, or it might indicate cryovolcanoes. Dawn also visited Vesta, which is the third largest but second most massive asteroid known. Vesta is round-ish, what's called an oblate spheroid, flattened a bit like a ball someone's sitting on. The southern hemisphere got hammered by impacts long ago, leaving a huge basin there. Several other main belt asteroids have been visited by spacecraft, mostly via flybys. Lutetia, Gaspra, Steins, Matilda. Ida is another and was discovered to have a small moon orbiting it. In fact, a lot of asteroids have moons, or are actually binary, with two similar-sized bodies in orbit around each other. Cleopatra, a weird dog-bone-shaped rock, has two moons. You might think asteroids are just giant versions of rocks you might find in your garden, tough, solid, singular bodies. But it turns out that's not the case. A few years ago, scientists realized that asteroids have spent billions of years whacking into one another, sometimes in high-speed collisions, sometimes more slowly. Slower hits can disrupt the asteroid, crack it, but not necessarily be strong enough to actually disrupt it so that it breaks apart. Over time, enough hits like that can leave behind what's called a rubble pile, individual rocks held together by their own gravity, like a bag of gravel, or a car window that's been cracked and still holds its overall shape. This became more clear when the Japanese Hayabusa spacecraft visited the asteroid Itokawa and saw what can only be described as a jumbled mess. The asteroid had no craters on it and was littered with rubble and debris. It was also very low density, just what you'd expect for a loosely bound rock pile. It's weird to think of some asteroids as being not much more than free-floating bags of gravel, but the universe is under no obligation to adhere to our expectations. It's full of surprises, and we need to keep our minds flexible. So here's a question. Why is there even a main asteroid belt at all? The solar system formed from a disk of material, and over time that material started to clump into bigger and bigger pieces. As planets formed, they swept up and pulled in lots more stuff and grew large. Jupiter consumed a lot of the material around it, but not all, and left a lot of debris inside its orbit. Some of this clumped together to form middling-sized objects, probably smaller than the planets we have now, but big enough to undergo differentiation. Heavy stuff like metals sank to the middle, and lighter stuff formed a mantle and crust. Collisions broke almost all of them apart, though, and that's why we see asteroids with different compositions. Some are from the denser core, others from the lighter crust. There was probably a lot more material between Mars and Jupiter billions of years ago, but it either got eaten by Jupiter or the planet's immense gravity altered the asteroids' orbits, flinging them away. This may be why Mars is so small, too. Jupiter robbed it of all of its food as it formed. While most asteroids live in the main belt, not all of them do. Some have orbits that cross that of Mars, taking them closer to the Sun. We call those, wait for it, Mars-crossing asteroids. Some have orbits that take them even closer to the Sun, crossing Earth's orbit. We call those Apollo asteroids. Gotcha! They're named after the asteroid Apollo, the first of its kind to be found. Some have orbits that are almost entirely inside Earth's orbit, called Aten asteroids. Aten and Apollo asteroids can get pretty close to Earth, so we call them near-Earth asteroids. Now, while they get close to us, that doesn't mean they'll hit us, because, for example, their orbits may be tilted, so their orbits and the orbit of the Earth don't actually ever physically cross. But Some do have paths that literally intersect Earth's. That doesn't mean they'll hit us every pass either. After all, you can walk across the street without getting hit by a car. The problem comes when you try to occupy the same volume of space as a car at the same time. Astronomers, unsurprisingly, are very concerned about asteroids that can hit us. That's why we have surveys, observatories, scanning the skies, looking for them. This is a pretty important topic, and I'll go into it in more depth in a future episode. There's another category of asteroid that exists due to a quirk of gravity. When a planet orbits a star, there are points along the planet's orbit and near it in space where the gravitational forces are in balance. If you place an object there, it tends to stay there, like an egg in a cup. These are called Lagrange points. One of them is along the same orbit as the planet, but 60 degrees ahead. Another is 60 degrees behind. The first such asteroid found was orbiting 60 degrees ahead of Jupiter and was named Achilles, after the Greek hero in the Trojan War. As more were found, the naming convention stuck. Asteroids ahead of Jupiter were named after Greek figures in the Trojan War, and those behind Jupiter were named for Trojans. And now we just call them all Trojan asteroids. Trojan asteroids have been spotted for Jupiter, Mars, Uranus, Neptune, and even Earth. Earth's was found in 2010 using observations by an orbiting observatory called WISE, which scans the skies in infrared light where asteroids glow due to their own heat. 2010 TK7, as it's called, is about 300 meters across and 800 million kilometers away, orbiting the Sun ahead of Earth. There are also asteroids that have orbits that are very similar to Earth's, but are slightly elliptical and tilted with respect to ours. Because of this, they can stay relatively near the Earth in space, but don't really orbit us. Instead, they sometimes get closer and sometimes recede. It's pretty weird, but a natural outcome of orbital mechanics. Some people say these asteroids are moons of Earth, but it's better to say they're co-orbital with us. Only a few are known, the most famous being Cruithne, which can get as close as 12 or so million kilometers from us. Oh, one more thing. Originally, asteroids were named after female goddesses, Ceres, Vesta, Juno, and so on. But as hundreds more were found, and then thousands, we ran out of names. Eventually, astronomers who discovered asteroids were allowed to name them through a lengthy proposal and acceptance process governed by the International Astronomical Union. They also get a number assigned to them as well. A lot of astronomers have asteroids named after them, including astronomers who study asteroids, like my friend Amy Mainzer, who works on the WISE mission. Hers is 234750 Amy Mainzer, and Eleanor Helene, who discovered quite a few asteroids and comets. Hers is 3267 GLOW for her nickname. And this one? It's a 1 kilometer wide rock in the main belt and goes by the name 165347 Phil Plate. Must be coincidence. Today you learned that asteroids are chunks of rock, metal, or both that were once part of I love astronomy, you may have noticed, but there's one really frustrating aspect of it. Everything we study is really far away. Nearly everything we understand about the universe comes from light emitted or reflected by objects. It'd be nice if we could get actual samples from them, physical specimens we could examine in the lab. Well, sometimes the universe can be accommodating and allows us to hold it in our hands. Cambot, can we get this up on StillStore? If you go outside on a clear, dark, moonless night, and you really should, chances are pretty good that within a few minutes, you'll see a shooting star. It'll zip across the sky, a fiery dot leaving a long glowing trail behind it. They're one of the most exciting and fun things you'll see when you look up, and they always get a gasp and a squeal of delight from someone who's stargazing. What you're actually seeing is a tiny bit of interplanetary debris. Rock, ice, or metal ramming through the Earth's atmosphere, heated to incandescence. Most are faint, but some can be astonishingly bright. I saw one once that left an afterimage on my eye. Obviously, shooting stars aren't really stars. So what do we call them? Sometimes it seems like astronomers use different names for objects to keep things as confusing as possible. But really, we do that to separate out different things. In this case, the actual bit of solid stuff coming from space is called a meteoroid. The phenomenon of the meteoroid getting hot and blazing across the sky is called a meteor. And finally, if it hits the ground, we call it a meteorite. I think the second best way to tick off an astronomer is to mix up meteor and meteorite. Sometimes astronomers can be pretty pedantic about such things. Oh, the best way to tick off an astronomer? Ask them, hey, what's your sign? Amazingly, a typical meteor that you'll see is due to a meteoroid that's tiny, probably smaller than a grain of sand. How can that be? It's because they're hauling mass. You heard me. The meteoroid is orbiting the sun, probably at speeds of a few dozen kilometers per second. As it approaches the Earth, our planet's gravity accelerates at an additional 11 kilometers per second, Earth's escape velocity. And when it enters our atmosphere, it's moving incredibly fast, up to 70 kilometers per second or more. The energy of motion is called kinetic energy. If you want to get something moving, you have to give it energy. And if you want it to stop, you have to take that energy away. This kinetic energy depends on the mass of the object and how fast it's moving. In fact, it depends on the square of the velocity. Double its speed and it'll have 4 times the kinetic energy. Meteoroids may usually be small, but they're screaming fast and have a huge amount of kinetic energy. As they hit our atmosphere, they slow from their ridiculous orbital speed to nearly a standstill, and all that energy has to go somewhere. It gets converted into light and heat, and that's what we see as a meteor. A big misconception about meteors is that they get hot due to friction with air. Actually, a far bigger contributor to their heat is compression. One of the most basic laws of physics is that when you compress a gas, it heats up. And a meteoroid coming in at hypersonic speeds compresses the air in front of it a lot, heating it hugely. The gas can reach temperatures of thousands of degrees Celsius for a few seconds. The air radiates away this heat, in turn heating up the meteoroid. The material on the surface vaporizes and blows away, a process called ablation. That ablated material leaves a glowing trail behind the meteor, which we call a train. Sometimes it can glow for several minutes, getting twisted up in high-altitude winds, leaving behind an eerie, ghost-like, persistent train. This all happens high above your head, about 90 to 100 kilometers above the ground. Typically, from any one location, you can see a few meteors per hour. It may not seem like much, but when you add them up all over the planet, you find the Earth is getting pelted to the tune of about 100 tons of material a day. But again, most of these meteoroids are teeny tiny. Those random meteors are called sporadic meteors. They tend to be rocky in composition and generally come from asteroids. If 2 asteroids smack into each other, the collision can eject little bits of material that then orbit the sun on their own. If their orbit crosses the Earth, then you have a potential meteor. It may take a few million years, but at some point, the Earth and the meteoroid are at the same place at the same time, and boom. But sometimes meteoroids travel in packs. When that happens, we can get meteor showers, many dozens or even hundreds of meteors per hour. With one exception, those don't come from asteroids. They come from comets. When a comet orbits the sun, the ice on it turns to gas, dislodging dust and gravel mixed in. This material leaves the comet and tends to stay more or less in the same orbit as the comet itself. Over time, that material gets scattered all along the orbit, creating a puffy ribbon of tiny pieces of space debris around the sun. When the Earth plows through that cloud of debris, we get a meteor shower. From our viewpoint on Earth, we see meteors shooting across the sky, apparently radiating away from a single point. That's a perspective effect. It's like driving through a tunnel and seeing the tiles on the wall and ceiling flying past you, all apparently coming from a point ahead of you. The point on the sky where the meteors come from is called the radiant, and the shower is named after the constellation the radiant's in. So we have the Perseid meteor shower, the Leonids, the Camelopardalids, or the Camelopardalids. And since the Earth hits a specific comet stream around the same time every year, the showers are annual. The Perseids are in August and the Leonids in November. Watching a meteor shower is easy. Just go outside and look up. Generally, they're better after local midnight. The Earth plows into the meteoroids, so facing the direction of Earth's orbital motion means more meteors, just like you get more raindrops on the front windshield of your car than on the back when you're driving through a storm. After local midnight, you're on the part of the Earth facing into the orbit, so you see more meteors. By the way, if you happen to be on the International Space Station, you have to look down to see a meteor. In 2011, astronaut Ron Garan photographed a Perseid burning up below him. But don't worry, the odds of the space station getting hit are extremely low. Space is big. Oh, and that one exception I mentioned before? That's the annual Geminid shower, which occurs in December. That comes from the asteroid 3200 Phaethon, which is on an orbit that takes it very close to the sun. It's possible it gets so hot that the rock vaporizes, making it act like a comet. The vast majority of meteoroids are small and tend to burn up in our atmosphere, but they can be bigger. A bolide, or fireball, is an extremely bright meteor, and those can be about the size of a grapefruit. Those happen pretty often somewhere over the Earth. I've seen a few myself. Very rarely, an incoming meteoroid will survive all the way to the ground and become a meteorite. Sometimes the immense pressure of ramming Earth's air causes the incoming meteoroid to crumble or even explode, raining down dozens or hundreds of smaller pieces. Typically, they slow rapidly after their blaze of glory and simply fall the rest of the way to the ground. The air up there is cold, and their interiors are cold from being in space so long. So, despite what you might think, meteorites don't cause fires when they hit the ground. In fact, they can be quite chilly. Meteorites are classified into three broad categories: stony, which are mostly rock; iron, which are mostly metal; and stony iron, which are a mixture of the two. The majority of meteorites we find are stony. The stony meteorites are themselves subdivided into two kinds: chondrites and achondrites. Chondrites contain chondrules, small grains of minerals. These are very primitive and are thought to have condensed out of the original disk of material that formed the solar system. Their ages can be found by looking at ratios of elements in them formed from radioactive decay. The oldest known meteorite formed 4.568 billion years ago, before the Earth itself formed. Achondrites don't have chondrules in them. Most likely they came from a bigger asteroid, one that was once molten all the way through, mixing the minerals. A big collision disrupted the parent body, creating the achondritic meteoroids. Iron meteorites most likely come from the center of a large asteroid, one big enough that metals fell to the center via gravity. Again, a big impact blew the asteroid up, scattering its material around the asteroid belt, and with some on orbits that eventually intersected Earth. Stony irons are the rarest. Some have green or orange crystals of a mineral called olivine embedded in a web of metal. Called pallasites, they may be the most beautiful of all meteorites. I actually collect meteorites. It's fun, but can be a somewhat pricey hobby. If you're interested, make sure you get them from a licensed dealer. We have links to some in the doobly-doo. Of course, on occasion, the meteoroid coming in can be a tad bigger. And when that happens, well, all hell can break loose. On February 15th, 2013, residents of the Russian city of Chelyabinsk got a rude awakening. At 9:20 a.m. local time, a rock about 19 meters across came in at a low angle. It got nearly as bright as the sun as it slammed into the atmosphere, and the pressure of its passage broke it up into several chunks, which broke up again. In a moment's time, the sudden energy released was equivalent to the detonation of 500,000 tons of TNT, as much as a small atomic bomb. While no one was killed, over 1,000 people were injured by flying glass, shattered by the explosion. No doubt they were at their windows gawking at the huge vapor trail in the sky when the shockwave hit. There was no warning for this event. The asteroid was essentially too small to detect while it was out in space. Well, for now at least. Telescopes are coming online soon that should be able to find smaller asteroids and give us some warning. Astronomers are more worried about ones roughly 100 meters across or bigger. These can do serious damage on a citywide scale or larger, but at the moment aren't easy to spot much in advance. And what do we do if we do see one headed our way? As of right now, there's not much we can do. Studies have been done to determine the best course of action, maybe lobbing a nuke at it or simply ramming it with a space probe to change the orbit and make sure it misses Earth. These ideas look good on paper, but they haven't been tested yet. We're still a few years from that. The good news is that objects that size hitting the Earth are rare, maybe once every century or three. But if we do nothing, it will happen eventually. As science fiction writer Larry Niven points out, the dinosaurs went extinct because they didn't have a space program. Hopefully, we're smarter than they were. Today you learn that meteors are small bits of interplanetary debris sloughed off by asteroids and comets. Hey, Phil Plait here, and this is Crash Course Astronomy. Since humans have been human, we've looked to the skies for portents of the future. The sun, the moon, the planets, the stars, they've all been used for prognostication. And so have comets. A fuzzy blob moving slowly across the stars? How could soothsayers resist? But now we know a lot more about comets. They're beautiful, fascinating, and can bring both life and death upon our little world.
One diaphragm per mankind.
Comets have been seen in the sky since antiquity. Comet Halley, for example, is shown in the Bayeux Tapestry, which depicts the Norman invasion of the British Isles in the year 1066. It was seen by ancient Chinese and Greeks, too. In general, and like everything else in the sky, comets were considered omens or harbingers of human events. Sometimes they were good omens. William the Conqueror liked his chances in 1066 after seeing one, and sometimes bad. That same comet didn't do so well for King Harold II. A comet bright enough to see with the naked eye shows up in the heavens every few years or so, and some can get spectacularly bright. In 2007, I saw Comet McNaught very near the sun in broad daylight. When you think of a comet, you probably picture a fuzzy blob and a long tail stretching away from it. Fair enough. But there's a bit more to them than that. Comets are in many ways similar to asteroids. They're roughly hewn chunks of stuff left over from the formation of the solar system. Unlike asteroids, which are mostly rock with a dash of ice and maybe metal, comets are a more balanced mixture of ice and rock. And by ice, I mean frozen water, but also frozen carbon dioxide, carbon monoxide, methane, ammonia, things we normally think of as gases on Earth. And by rock, I do mean rocks, but also gravel and dust. In fact, astronomers sometimes call comets dirty snowballs, which isn't a half bad term. It's that ice that makes comets, well, comets. When they're way out in deep space, they're so cold that they're basically inert lumps of ice and rock. But many are on elliptical orbits that take them from those sub-freezing depths into our neck of the woods where the sun can warm them. As they heat up, the ice turns directly into a gas, a process called sublimation. The gas then flows away from the comet, creating a cloud around it. This makes the comet look fuzzy, and actually in the past they've been called hairy stars. I like that term too, and in a sense we still use it. The solid part of the comet is called the nucleus, and the gaseous cloud around it is called the coma, Latin for hair. In fact, that's why we call them comets. As the ice sublimates, the bits of rock and gravel and dust embedded in it can be freed and leave the nucleus as well. This material is what forms the comet's tail, but how that happens depends on which material you're talking about. The gas and the dust from comets form two different tails. Gas molecules emitted by the comet get ionized by the sun's ultraviolet light. That means they lose electrons, becoming charged, and charged particles are highly susceptible to magnetic fields. The solar wind is a stream of charged particles blown out by the sun and carries a magnetic field with it. As the wind hits the ionized gas from the comet, it picks up those particles and carries them downstream, away from the sun. The solar wind is usually moving far, far faster than the comet, so this ion tail winds up pointing directly away from the sun. The dust, on the other hand, is influenced more by sunlight. Light from the sun exerts a small but inexorable pressure, and this pushes on the dust particles. The dust streams away, but because the pressure isn't as intense as the solar wind is on the gas tail, the dust tail blows away more lazily and tends to lag behind the comet in its orbit. That means the two tails usually point in two different directions. In some comets, like 1997's incredibly bright and gorgeous comet Hale-Bopp, this is pretty obvious. The dust tails look white or a teeny bit yellowish due to reflected sunlight, while the ion tail glows blue or green depending on the primary constituents of the gas. Carbon monoxide tends to emit blue light, while carbon molecules glow a ghostly green. A comet's tail can stretch for tens of millions of kilometers, but despite their length, tails are incredibly low density, as low as a few hundred atoms per cubic centimeter. The air you breathe is 1,000,000 billion times denser. In 1910, Earth passed through the tail of Comet Halley. This caused some public fear because cyanogen, a deadly gas, had been detected in the tail. But of course, nothing happened. It turns out getting a gazillionth of the toxic dose isn't that big of a problem. Broadly speaking, comets are classified by their orbits. If they have orbital periods less than 200 years, they're called short-period comets. These tend to orbit the sun in the same plane as the planets and go around the sun in the same direction as well. From Earth, we see them sticking near the ecliptic, the line across the sky that marks the annual path of the sun. Comets that take longer than 2 centuries to go around the sun are called long-term comets and have orbits that are tilted every which way. That means they can appear anywhere in the sky. But this raises an interesting point. Comets go away. Every time they get near the sun and start outgassing, they lose mass. Over time, they get smaller. Eventually, they should evaporate. Some do this all at once because they dive into the sun, skimming our star's surface. We call those sun divers or sun grazers. Many of those may actually be pieces from a bigger comet that broke up in space nearly 1,000 years ago. But besides those, we know of some comets with orbits that can be short, some with periods of just a few years. Even a century is like a single flap of a mosquito's wing compared to the lifetime of the solar system. How can comets be billions of years old if their orbits bring them close to the sun all the time? Astronomers wondered about this very thing. Over the years, they came up with an idea. Maybe out past Neptune, there's a repository of comets, chunks of dirty ice, millions of them, billions, orbiting the sun where it's perpetually cold. They could have orbits that last for millennia or more, but then something tweaks them, makes them fall toward the sun. In fact, there may be 2 such regions, since we have both short period and long-term comets. Turns out, this is correct. We now know enough about those distant regions of the solar system that they deserve their own episode, so we'll dive into that topic later. So, what do comets look like up close? Like really close. Studying them from Earth is hard. The coma obscures the nucleus, making it nearly impossible to see it directly. From Earth. If you instead send your telescope to a comet, things change. We first did that in the 1980s, the last time Comet Halley came around. Several nations sent spacecraft to fly past the comet, and the Soviet mission Vega 1 was the first to successfully get pictures of the nucleus. The low-resolution images revealed a dark lump highlighted with two bright spots, later determined to be jets of gas streaming away. These images were used to better determine the position of the nucleus, and a few days later, the European probe Giotto zipped past the nucleus at an incredibly close distance of just 600 kilometers. Those pictures were more detailed and showed us a flying mountain in a regular chunk 15 by 8 kilometers in size. And it was dark, reflecting only 4% of the light that hit it. That makes the nucleus as black as asphalt. You might think that all that ice would be shiny, but it's not that simple. Most of Halley's nucleus is covered in thick dust laced with darker molecules, with only a few spots emitting gas. Most likely there are deposits of ice under the surface, and only some of them receive enough heat from the sun to sublimate and blow out gas. This has been seen with other comets as well. The gas is emitted from specific spots on the comet, venting out from cracks in the crusty surface. The surfaces of comets must be inhomogeneous, different in different places. That fact was brought home magnificently in 2014 by another European mission, Rosetta. It went into orbit around the comet 67P Churyumov-Gerasimenko and found it to be a bizarre little object. Measuring about 4 kilometers end to end, 67P has two lobes connected by a narrow neck, looking very much like a cosmic rubber ducky. The surface is completely devoid of craters. Clearly, the surface is very young. Images show jets of gas emitted from very specific places on the surface, and there are wide circular pits here and there, which may be gas vents, growing wider over time as the ice below is depleted. Surprisingly, the surface is fairly tough and hard, when some scientists expected it to be fluffier. The comet has a very low density, similar to rubble pile asteroids, so it was expected that the surface would be soft. Rosetta sent down a lander named Philae to set down on the surface, using harpoons to anchor itself, but instead the lander bounced, unable to penetrate the tougher than expected material. One idea to explain this is that the ice is porous and fluffier inside the comet, but as it nears the sun, the ice at the surface warms and changes its structure, forming that harder crust. As for the double lobe thing, well, that's a bit baffling. We see some asteroids shaped that way as well. It's possible 67P used to be two separate comets that had a low-speed collision and stuck together. Or maybe it used to be one big lump, but over the eons, the ice in the middle sublimated more, leaving behind the two lobes. Rosetta is the first time in human history we've had a probe orbiting a comet, studying it up close and long term. We're still learning, still figuring this stuff out. Incidentally, I mentioned earlier that A, comets have lots of ice in them, and 2, they also get really close to Earth sometimes. In fact, they can hit us. Now, not to get all technical and scientific-y, but that is what we would call bad, as we'll discuss in an upcoming episode. But billions of years ago, lots of comets hit the Earth not long after our planet formed. Together with asteroids, many of which are also rich in water ice, they may have brought a significant amount of water to Earth. Scientists are still wrestling over the details of this, and it may be a while before the actual numbers are nailed down, but it's an intriguing thought. Even more interesting, in 2004, NASA's Stardust space probe physically passed through the coma of comet Wild 2, collecting samples that were returned to Earth. Careful analysis of the material found the presence of organic, carbon-based molecules in them, and not just any random molecules, but complex ones, including amino acids. These are the building blocks of all life on Earth. Amino acids are what our bodies use to create proteins. It's possible that the ingredients of life on Earth didn't start here, but instead were brought to our planet from comet impacts, or at least there was a mix of the two. If that's the case, then in a sense, all life on Earth is part alien. How about that? But what gets me are the philosophical ramifications of this. When we look into space, when we examine our celestial neighbors, when we send probes to comets and survey what we find, we're looking at our own origins. Comets are like time machines, allowing us to investigate our past 4 billion years back, hinting at the secrets of the origin of life itself. And you thought astronomy was just lying out in a field and looking up. Well, it is, but if you let it, it's also a whole lot more. Today you learn that comets are chunks of ice and rock that orbit the sun. When they get near the
So hopefully that will provide a quick overview of what we will be discussing today. Do you guys have any questions so far? Okay, cool. So for this lecture, as seen in the video, we're going to discuss meteoroids, meteors, meteorites. Are you guys still familiar with what is the difference between them? So this is a hint, a question I like to ask in the test and exams. We've discussed it last week as well. So it's a meteoroid. Before I discuss it, let's see, what do you guys think is a meteoroid? So it's called a rock in space before entering the atmosphere. That is correct. And a meteorite. Yes. So remember, the chunk that survived its journey through the atmosphere is called a meteorite. If it travels through the atmosphere, it's a meteoroid with a D. And if it's in space, then it's a meteor. You guys happy with those definitions? Awesome. So this is how a asteroid containing iron will look like if it landed on Earth. And you can see the iron content is melted in this image. So here we can see a few of the biggest asteroids in the asteroid belt. So the videos explain the work quite nicely. So I'm going to give an overview of the slides for this lecture. This is how a comet will look like in space. So if you've actually seen the comet before. So there's actually a comet now visible that you guys can see with the unaided eye. I will provide information on it and post it on the announcements. But yes, you can actually see a comet right now. So for this lecture, we need to answer 4 important questions. Firstly, where do meteors and meteorites come from? Secondly, what are asteroids? Thirdly, what are comets? And lastly, what happens when asteroids and comets hit Earth and other planets? So something interesting, there's only one person in recorded history that has been hit by an asteroid, and that was in 1954, while Mrs. E. Hewlett Hodges of Alabama lay napping on a living room couch. An explosion and sharp pain jolted her awake. Analysis of the brick-sized rock that smashed through the ceiling and bruised her left leg showed it was a meteorite. Mrs. Hodges is the only person to have been injured by a meteorite. Coincidentally, she lived right across the street from the Comet Drive-Thru Theater, which is quite ironic. But do you guys actually believe it's that one person in history has been hit by a rock. So when we look at some of these meteorites in Earth's atmosphere, some of them travels at about a speed of 10 to 70 kilometers per second, which is quite fast. And the streak you see is actually due to friction with Earth's atmosphere. That's causing them to heat up and burn. Some of them vaporize, and that is what people commonly refer to as shooting stars, the streak and light. Some of them makes it to the ground, others burns up in the Earth's atmosphere. So, surprisingly, one of the best places to look for asteroids is in Antarctica. Do you guys know perhaps why? No, nothing to do with Earth's salt. Also, nothing to do with everything is white. It's because the environment doesn't really change. Say, for example, where we are in Pretoria, if a meteorite hits the ground, how difficult will it be to find it on the ground? Quite difficult, because remember, you have buildings, you have natural parks, you have woodlands, you have mountains. So even if you track the trajectory quite easily, it's very hard to find. But in Antarctica, because the environment is basically desolate, it's quite easy to find asteroids and meteorites. So roughly 40,000 meteorites has been collected from Antarctica. Does everybody understand the statement I made? Awesome. So in this image, you can see some larger meteorites that has been collected from Antarctica. So something interesting is, do you guys know you can actually go work in Antarctica for a year? So every year there's a crew change in Antarctica. So there's a international research base or research facility, a better word is research base, that you can work for a year. It is very well paid, and they provide you with food, they provide you with housing and clothing for that duration. The only thing is, to be able to qualify for it, you need to at least have a honors degree, and you have to be physically and mentally strong enough for it. So you go through physical and psychological tests, and if you pass, then you, at usually around about December, the SAS Gullas comes and pick you up. You guys know what the SAS Gullas is? So South Africa actually has two ships, the SAS Gullas 1 and the SAS Gullas 2, and they are research vessels. So the whole ship is basically one giant lab, and they are usually months on end at sea conducting research. So the SAS Gullas 1 or the SAS Gullas 2 will pick you up from Cape Town. Then from Cape Town, it's about a month's journey to Antarctica. Then they drop you off in Antarctica. You stay there and conduct research for a year and work on the base. And then the following December, the SAS Gullas comes and pick you up again and brings you back to South Africa. And then you have a crew change. So if you are interested in something, Google it. They're usually looking for new crew each year to man the station. You can also work on the SAS Agulhas as well. So it's important. This is also a question I like to ask for the exam, is what are the three broad composition categories of meteorites? The first is iron meteorites, the second is stony iron meteorites, the thirdly is stony meteorites, and then there's a fourth one called carbonaceous chondrites. So in this image, we can see how these differ. So here we can see in the top left, this is a iron. So here we can see is a stony iron. Right here is a stony meteorite, and here we can see is a chondrite. All four of them. So iron meteorites make up only 6% of the meteorites witnessed falling from the sky. So you can estimate that only 6% of meteoroids traveling through space near Earth have an iron composition. You might wonder, why do iron meteorites make up 66% of meteorites found on the ground? And that is because iron meteorites don't look like ordinary rocks. They are easy to recognize because they are heavy, dense lumps of metal. So if you trip over one on a hike, you are more likely to recognize it as something odd. Carry it home and show it to the local museum. Also, some stony meteorites deteriorate rapidly when exposed to weather. Irons are made of stronger material and generally survive longer. The recognizability and durability of iron meteorites means there is a selection effects that makes it more likely to be found than other types of meteorites. Do you guys understand that? Awesome. So when we take iron meteorites and we cut them open and polish them, we would see interesting bands on them called Wittgenstein bands. And that is caused by alloys in iron and nickel that form crystals in a molten metal and cooled and solidified. And the size and shape of the bands indicate the molten metal cooled very slowly, indicating a location inside bodies at least 30 kilometers in diameter. And on the other hand, these iron meteorites do not show effects of very high pressures that would exist deep inside a planet. Evidently, iron meteorite material formed in the cooling interiors of planetesimal-sized objects, smaller than planets. And this is one important clue to meteorites. In contrast to irons and stony meteorites are common among meteorites seen falling to Earth. Although there are many different types of stony meteorites, you can classify them into two main categories depending on their physical properties and chemical content: chondrites and achondrites. Chondrites look dark gray, granular rocks, and in general, chondrites contain some volatiles, including water and organic compounds. A few chondrites evidently formed in the presence of liquid water, and most types of chondrites also contain chondrules, small round bits of glassy rock only a few millimeters across to be glassy rather than crystalline. And chondrules must have cooled from molten state quickly within a few hours. One hypothesis is that chondrules are bits of matter from the inner part of the solar nebula, near that were blown outward by winds or jets to cooler parts of the nebula, where they condensed and were later incorporated into larger rocks. Another hypothesis is that the chondrules were once solid bits of matter that were melted by shock waves spreading through the solar nebula and then re-solidified. Among the chondrites, the carbonaceous chondrites are a rare but quite important subtype. These dark grey rocky meteorites are especially rich in water, other volatiles, and organic compounds. And those substances all would have been lost if the meteoroid had been heated and to a room temperature. Medicarbonaceous chondrites also contain small irregular inclusions rich in calcium, aluminium, and titanium called CAIs for calcium aluminium rich inclusions. These bits of matter are highly refractory. That is, they vaporize or condense only at very high temperatures. If you could scoop out a portion of the sun's photosphere and cool it, the first particles to solidify would have the chemical composition of CAIs. As the temperature fell, other material would become solid in accord with the condensation sequence described in Chapter 15, Section 3. So when we talk about the orbits and origins of meteoroids, a typical meteoroid has roughly the mass of a paperclip and vaporizes at an altitude of about 80 kilometers above Earth's surface. And a meteor trail points back along the path of the meteoroid. So if you study the direction and speed of meteors, you can get clues to their orbits in the solar system before they encountered Earth. So at the Hartebeeshoek Observatory, we have a camera system that continuously tracks the night sky to look for meteorites. And there's two reasons for that is. Then we have software that calculates the trajectory. So if it doesn't burn up, we can go and collect them. And we also use the trajectory to see where it came from, to see if it perhaps can track the origin of that specific meteorite that has hit the ground. And then also, who of you have seen meteor showers? So meteor showers are usually called after the constellation from which they seem to radiate from. And there's actually two meteor showers we can see every year. So how it happens is we have Earth in a sun orbit, and here is the orbit of a comet. And each time Earth moves through this band that a comet loses. So in image A is a meteors in a meteor shower enters Earth's atmosphere along its parallel paths. But perspective marks appear to diverge from a single point in the sky. Then in image B, a similar parallel railroad tracks appear to diverge from a point on the horizon. And in C, meteors in showers are debris left behind by the comet's icy nucleus vaporizes. And the rocky metallic bits of matter spread along the comet's orbit. Even if Earth passes through such metal radiate, you can see a meteor shower. So usually there's one you can see around about April, and another one you can see 6 months later in about October. If you are in residential areas, you could see between 4 and 6 per hour. If you are in darker skies, you could see upwards to 30 meteors per hour, which is actually very cool. So when we look at this image, it shows the origin of meteoroids. So some of the planetesimals that formed early in the solar system's history may have differentiated, that is, melted and separated into layers of different density and composition, as did terrestrial planets. So you're all familiar with the differentiation process that we talked about in last week's class, correct? Awesome. So in some cases, some of those planetesimals could be fragmented, and that can produce different types of meteorites. So asteroids are a bit different than meteorites. So asteroids are distant objects too small to study in detail with Earth-based telescopes. And astronomers nevertheless has learned a surprising amount about those little worlds using spacecraft and space telescopes. So evidence from meteorites show that asteroids are the last remains of the rocky planetesimals that built the terrestrial planets 4.6 billion years ago. So notice 4 important points and 3 new terms. Most asteroids are irregular in shape and battered by impact cratering, and many asteroids seem to be rubble piles of broken fragments. Secondly, some asteroids are double objects or have small moons in orbit around them. This is further evidence that asteroids have suffered collisions. Thirdly, a few asteroids show signs of geological activity that probably happened on their surfaces when those asteroids were young. And then lastly, asteroids can be classified by their albedos, colors, and spectra to reveal clues to their compositions. So what is meant about the albedos of an object in space? So the albedo is the amount of light reflected from its surface. So if the sun shines on it, how much light is reflected? So this also allows them to be compared to meteoroids in labs on Earth. And we get C-type, S-type, and M-type asteroids. Those are the main classes discovered by this method. So the first ever asteroid was discovered in 1801 by Sicilian monk Giuseppe Piazzi and later named Ceres. And astronomers were excited by Piazzi's discovery because Ceres orbits 2.8 AU from the Sun in a wide gap between Mars and Jupiter, where it was thought the planet ought to be. But Ceres has less than 1/4 the diameter of Earth's moon, much smaller than any of the planets. 3 even smaller objects, Phalas, Juno, and Vesta, were discovered within a few years, all orbiting between Mars and Jupiter. So astronomers decided Ceres and the other asteroids should not be considered true planets. You learn in chapter 18, section 6, that Ceres, the largest object in the asteroid belt, has now been reclassified as a dwarf planet because it has enough gravitational strength to squeeze itself into spherical shape, but not enough to have swept up or cleared away the rest of the asteroids. Today, more than 400,000 asteroids have well-charted orbits. Other than dwarf planet Ceres, only 3 are larger than 400 kilometers in diameter, and most are much smaller. There are probably 1 million or more that are larger than 1 kilometer in diameter. Astronomers are sure that all the large asteroids in the asteroid belt have been discovered, but are also sure that many small asteroids remain undiscovered. Movies and TV have created a common misconception that flying through an asteroid belt is an hair-raising plunge requiring constant dodging left and right. The asteroid belt between Mars and Jupiter is actually mostly empty space. In fact, if you were standing on an asteroid, it would be many months or years between sightings of other asteroids. So something that we do with these asteroids, so some of them that's near Earth and could be potentially dangerous to Earth, we call them near-Earth objects, or NEOs. And the most dangerous type of these NEOs, those of them that crosses Earth's orbit, are called Apollo objects, after the first such asteroid discovered. And the combined searches estimated to have found at least 93% of the Apollos and other NEOs larger than 1 kilometer in diameter, and are now focused on finding a similar percentage of objects down to the size of 150 meters. In March 2009, NEO searchers spotted a small asteroid 2 to 3 meters in diameter, about the size of a small truck on a collision course with Earth. Astronomers were able to observe it in space before impact and discovered that its color and albedo matched a type of asteroid found mostly in the outer belt. The asteroid entered Earth's atmosphere over the deserts of southern Sudan, exploded. Scientists from the United States and Sudan searched for pieces of the object. So in this image, we can see the diagram plots the position of known asteroids between the Sun and the orbit of Jupiter on a specific day. And most asteroids are in the main belt. Squares, filled or empty, show location of known comets. Although asteroids and comets are small bodies and lie far apart, there are a great many of them in the inner solar system. So the ones in the green are main belt asteroids that lie between the orbits of Mars and Jupiter. The ones in red are asteroids that could approach Earth and are shown in red. And then these on the outside of the main asteroid belt are called Trojan asteroids. And they orbit in two areas, 60 degrees ahead of Jupiter and 60 degrees behind Jupiter. So this is the team that found one of the fragments in Sudan. So what I found was a 4-kilogram piece of fragments corresponding to a rare type of stony meteorite. And for the first time, a definite connection could be made between an asteroid observed in space and meteorites with properties measured in Earth's laboratories. In 2010, a Japanese probe Habashua returned a capsule to Earth containing a few tiny grains from the surface of an S-type asteroid Itokawa, which were found to be chemically identical to one of the most types of ordinary chondrite materials, or meteorites. There are other non-belt asteroids beyond the main belt, and gravitational effects of Jupiter and the Sun combine to trap the two asteroids in the Lagrange points that are 60 degrees ahead of and 60 degrees behind the planet's orbit. And these are called Trojan asteroids because individual objects have been named after heroes of the Trojan War. Astronomers have also found a few objects in the Lagrange point of the orbits of Mars and Neptune. The object Sirion found in 1977 is about 170 kilometers in diameter. Its orbit carries it from the orbit of Uranus to just inside the orbit of Saturn. Objects like Sirion with orbits between or crossing orbit of the Jovian planets are called centaurs. Although it was first classified as an asteroid, Sirion later surprised astronomers by suddenly releasing jets of water vapor and dust. And you will learn in the next section that this more resembles characteristics of comets than asteroids. So centaurs show that the distinction between asteroids and comets is not clear-cut. As technology allows astronomers to detect smaller and more distant objects, they are learning that the outer solar system contains large numbers of these small bodies. The challenge is to explain their origin. So an old hypothesis proposed that asteroids are the remains of a planet that exploded. Planet-shattering death rays may make for exciting science fiction movies. But in reality, planets do not explode. The gravitational field of a planet holds the mass together so tightly that completely disturbing the planet would take tremendous energy. In addition, the present-day total mass of asteroids is located only about 1/20 of the mass of Earth's moon. So hardly enough to be the remains of a planet. So look back at the figure that opens chapter 15 to see an extrasolar planetary system with an asteroid belt interior to the orbit of the Jovian planet. And that arrangement have the same cause in our solar system. Astronomers have evidence that the asteroids are the remains of material lying 2 to 4 AU from the Sun that was unable to form a planet because of the gravitational influence of Jupiter. The next planet outward, over the 4.6 billion year history of the system, most of the objects originally in the asteroid belt have collided, fragmented, and been covered with craters. Some asteroids were perturbed by the gravity of Jupiter, and other planets into orbits collided with planets or the Sun, caused them to be captured as planetary satellites or ejected them from the solar system. And these present-day asteroids are understood to be very minor remnants of the original mass in that zone. So in this image, we can see in image A, this is image of the asteroid Vesta, made from a distance of 2,000 kilometers by the NASA Dawn spacecraft. And it shows Vesta's south polar region, which is dominated by the Recife impact basin. And then image B, dwarf planet Ceres, the largest object in the asteroid belt between Mars and Jupiter. And the prominent white spots may be salt deposits left by evaporating water. So one thing also before we start the discussion with comets is, do you guys actually know that Jupiter protects Earth from the majority of asteroid strikes? So that is because Jupiter has such a gravitational pull. If an asteroid comes loose in an asteroid belt, or a Trojan comes loose, or something new enters the solar system, Jupiter's gravitational field will catch them. So Jupiter is a big protector of Earth. If it wasn't for Jupiter, we might have had a few catastrophic extinction events, such as the dinosaurs extinction level event with asteroids, and Jupiter shields us from them. So the next object we need to talk about is comets. So few sights in astronomy are more beautiful than a bright comet hanging in a night sky. It is a common misconception that comets whiz rapidly across the sky like meteors. Actually, a comet's motion is hardly apparent. Night by night, its position shifts slightly against the background stars. It may remain visible for months. While everyone can enjoy the beauty of comets, astronomers study them because they are messengers from the past, carrying cargoes of information about the origin of the solar system. Always, as you begin with your study of a new kind of object by summarizing its observational properties. What do comets look like and how do they behave? So notice three important properties of comets plus three new terms. The first one is, comets have two kinds of tails, shaped by the solar wind and solar radiation. Gas and dust released by a comet's icy nucleus produce a head or a coma, and are blown outward away from the sun. And the gas produces a tail, and the dust produces a separate dust tail. Secondly, comet dust produces not only one of the two types of comet tails, but also spreads throughout the solar system. And some of those comet dust particles later encounter the Earth and are seen as meteors. And thirdly, evidence shows that some comet nuclei are fragile and can break into pieces. So the nuclei of comets are quite small and cannot be studied in detail using Earth-based telescopes. Nevertheless, when a comet nucleus approaches the Sun, it emits material that form into a coma or head, and a tail that can be millions of kilometers in size and is easily observed. The spectra of a comae, plural of coma, and tails indicate nuclei must contain ices of water and other volatile compounds such as carbon dioxide, carbon monoxide, methane, ammonia, and so on. These are the kinds of compounds that would have condensed in cold regions in the solar nebula. This convinces astronomers that comets are ancient samples of the gases and dust from which the outer planets formed. As the ices absorb energy from sunlight, they sublime, change from solid into a gas. The gases break down and also combine chemically, producing other substances found in comet spectra. For example, vast clouds of hydrogen gas observed around the heads of comets are understood to derive from the breakup of ice molecules. 5 spacecraft flew past the nucleus of Comet Halley when it was visited its inner solar system in 1985 and 1986. Other spacecraft flew past the Comet Borlée in 2001, Comet Wood 2 in 2004, and Comet Tempel 1 in 2005, and Comet Hartley 2 in 2010. Images show that all these comets' nuclei are 1 to 10 kilometers across, similar to the size of mini asteroids, and also irregular in shape. In general, these nuclei are darker than a lump of coal, which suggests composition similar to the carbon-rich carbonaceous chondrite meteorites described earlier in this chapter. So, the mass and density of comet nuclei can be calculated from the gravitational influences on passing spacecraft. And comet nuclei appear to have densities between 0.1 and 0.25 grams per cubic centimeter, much less dense than the density of ice. Also, you will learn later in this chapter, comets subjected to tidal stresses from Jupiter and Sun or the Sun come apart very easily. Comet nuclei have been described as dirty snowballs or icy mudballs, but it seems to be incorrect. Their shapes, low densities, and lack of material strength suggest that comets are not solid objects. The evidence leads astronomers to conclude that most comet nuclei must be fluffy mixtures of ices and dust with significant amounts of empty space. On the other hand, images of the nucleus of Comet Wild 2 reveals cliffs, pinnacles, and other features that show the material has enough strength to stand against the weak gravity of a comet. So here we can see different images of comets and how they compare. So here we can see the nucleus of Comet Hartley, the HST image of Comet Hale-Bopp, and so on. So in this image, we can actually see some of the structures on asteroids. So one of the most famous landing was the landing of the Rosetta spacecraft on a portion of the comet. So here we can see the red ellipse that's shown on this image is 16 by 150 meters and marks the likely location of the Philae lander determined by Rosetta's CONSORT radar experiment. And then in image B, it shows the view of the comet's surface from Philae, showing a small cliff or large boulder approximately 4 meters tall, directly in front of the probe. The end of the lander's free landing legs can be seen in the foreground. So here we can see one of the legs. Family relationships among the comets can give you clues to their origin. Most comets have long elliptical orbits with periods greater than 200 years and are known as long period comets. The long period comets' orbits are randomly inclined to the plane of the solar system. So those comets approach the inner solar system from all directions. Long period comets revolve around the Sun in about an equal number of prograde orbits, meaning the same direction in which the planets move, and retrograde orbits. In contrast, about 100 or so of the 600 well-studied comets have orbits with periods less than 200 years. These short period comets usually follow orbits that lie within 30 degrees of the plane of the solar system. Most revolve around the Sun prograde. Comet Halley, with a period of 76 years, is an unusual short period comet with a retrograde orbit. A comet cannot survive long in an orbit that brings it into the inner solar system. The heat of the Sun vaporizes millions of tons of ices during each passage and reduces comets to inactive bodies of rock and dust. Such comets can last at most 100 to 1,000 orbits around the Sun. Astronomers calculate that even before a comet completely vaporizes from solar heating, it can't survive more than about 500,000 years crossing the orbits of the planets, especially Jupiter, without having its path rerouted into the Sun or out of the solar system or colliding with one of the planets. Therefore, comets visible in our skies now can't have survived in their present orbits for 4.6 billion years since the formation of the solar system. And that means there must be a continuous supply of new comets. So where do they come from? In the 1950s, astronomers Jan Oort proposed that the long-period comets are objects that fall inward from what is known as the Oort cloud, a spherical cloud of icy bodies that extend from about 10,000 to 100,000 AU from the Sun. Astronomers hypothesized that the Oort cloud objects were originally planetesimals formed in the outer solar system that were tossed to their current distant locations by the gravitational influence of the growing Jovian planets. The Oort cloud is estimated to contain 7 trillion icy bodies far from the Sun, and are very cold, lack coma and tails, and are invisible from Earth. Astronomers calculate that some Oort cloud objects can be perturbed by the gravitational influence of passing stars, so they fall into the inner solar system. There, the heat from the Sun warms their ices and transforms them into comets. The fact that long-period comets are observed to fall inward from all directions is explained by the Oort cloud reservoir being spherically distributed around the Sun and inner solar system. A few short-period comets, including Comet Halley, also seems to have originated as long-period comets from the Oort cloud, and then had their orbits altered by a close encounter with Jupiter. However, that process can't explain all the short-period comets. The Kuiper belt, which you first encountered in chapter 15, section 2, when you initially surveyed the solar system, is another source for icy bodies passing through the inner solar system. Kuiper belt objects orbit in the same directions as the planets and in the plane of the solar system. Mathematical models show that it is likely for Kuiper belt objects perturbed inward by the influence of the giant planets to move into an orbit resembling those of the short-period comets. Comets vary in brightness and orbit. Nevertheless, there are two basic types of comets in our solar system. Some originate in the Oort cloud far from the Sun, others come from the Kuiper belt just behind Neptune. They all share one characteristic. They are ancient icy bodies that were born when the solar system was young. So the last thing we need to talk about is asteroid and comet impacts. So most meteors are small particles ranging from a few centimeters down to microscopic dust. And astronomers estimate that Earth gains about 40,000 tons of mass per year from meteoroids of all sizes. So that is actually quite amazing. 40,000 tons are added to Earth's mass each year due to impacts from space. So that is actually very cool. Don't know if you guys have actually realized this. So we have actually detected a few of these impact craters. So the first one is perhaps the Barringer crater near Flagstaff, Arizona. And that is 1.2 kilometer in diameter and 170 meters deep. And Eugene Schumacher proved in his 1963 doctoral thesis that a crater must be the result of an impact rather than volcanic eruption, because quartz crystals in and around it had been subjected to pressures much higher than can be produced by a volcano. And further study shows that a Barringer crater was created approximately 50,000 years ago by a meteoroid estimated to have been 50 meters in diameter, as large as a good-sized building. And that hit at the speed of 11 kilometers per second, releasing as much energy as a large thermonuclear bomb. And an asteroid of that size could be called either a large meteoroid or a small asteroid. Debris at the site shows that the impactor was composed of iron. So here we can see it. You guys actually know there are two big impact craters in South Africa that you can visit. So can you name the two? So the one is on the border of Gauteng and the Free State, the town called Parys. There is called the Vredefort Dome, on Afrikaans die Vredefort Koepel. That is the biggest asteroid impact crater in South Africa. You can actually see on Google Maps the crater and the ring fringes. And then just north of Pretoria, there's also a impact crater. No, I can't remember what's name. Let me quickly search. That's the Twain crater. It's north of Pretoria. It's also formed part of the Twain Natural Reserve. Just one thing is, you can go. Okay, so let me provide you with the one. So, come on. So this is the one, and the other one is the Vredefort crater. So the one thing I can just select, if you try to visit the Twain crater, do it in a group. Unfortunately, the hiking trails there has become quite a hotspot for muggings. The one in Vredefort is much safer. So you can read up about it and perhaps get some friends together and visit it. So there have been, in the last 100 years, quite recent hits. So on a summer morning in 1908, reindeer herders and homesteaders in central Siberia were startled to see a brilliant blue-white fireball, brighter than a sun streak across the sky. Still descending, it exploded with a blinding flash and an intense pulse of heat. The blast was heard up to 1,000 kilometers away, and resulting air pressure circled the Earth twice. When members of the scientific expedition arrived at the site in 1927, they found that the blast occurred above the stony Tunguska River Valley and it knocked down trees pointing away from the center of region about 30 kilometers in radius. So this was happens. That was one of the most dangerous impacts in recent years. So no crater has been found at the Tunguska site, so it seems that the explosion, estimated to have equaled 12 megatons of TNT, and occurred at least a few kilometers above ground. A detailed analysis of all the available evidence suggests that the impact's speed and direction resembles the orbits of Apollo objects. Astronomers produced computer models of objects entering Earth's atmosphere concluded that the most likely candidate for the Tunguska object is a stony asteroid about 30 meters in diameter, perhaps 1/10 the mass of the Barringer impact. An object of this size and material strength would have fragmented and exploded at just about the right height to produce the observed blast. This concussion, and consistent with the modern studies of the Tunguska area, showing that thousands of tons of powdered material with composition representing carbonaceous chondrites are scattered in the soil. So to think that is what happens with an object 30 meters in diameter. So that is why it's important that we track these objects. And that is also important why we need to find a way to defend Earth from these objects. And 2 years ago, NASA did their first impact test. So the easiest way to protect Earth is to change the orbit of these asteroids or meteors a little bit. And one thing you do it, you either slow down the orbit of an asteroid or you speed it up. And they sent a spacecraft into the asteroid field to test this hypothesis, and it crashed into the surface, and with this crash was calculated to speed the orbit a little bit up. So we have proved that we can change the orbit of asteroids. So that is why it is important for us to track these near-Earth objects. So also we can see other hits as well of asteroids. So one recently was in 2009 when there was an impact on Jupiter, and we could pick it up with our telescopes, and afterwards it left these marks on Jupiter that we can see, which is quite amazing. And that brings us to discussion of planet-shaking events that we need to protect ourselves. So one of these major events or major strikes on Earth was 65 million years ago when the dinosaurs were wiped out. And that changed the extinction event. So this is a hint for test and exams. What I usually ask every exam, what caused the dinosaurs to become extinct? And the reasons for that is, listen carefully. The asteroid hit Earth. It knocked up a lot of dust. The dust circulated up in Earth's atmosphere, blocking out the sunlight, which caused Earth to cool down. So when Earth cooled down, it caused that plants died because they cannot make use of this photosynthesis method. When the plants died, the herbivores died. When the herbivores died, there's nothing to eat for the carnivores, and the dinosaurs became extinct. That's one of the reasons. The other reasons is because of the cooled climate, it created a cosmic winter. So the actual impact didn't kill the dinosaurs. It's the secondary impact. And that is lack of food, and it cooled down the climate. You guys understand that? Awesome. So the impact crater that killed the dinosaurs is called the Chicxulub impact crater, and it happened in the northern Yucatan region of Mexico. And the crater is 180 kilometers in diameter, and the object that hit that area is estimated to be between 10 and 15 kilometers in diameter, so quite a very large object. So if you look here, the Gulf of Mexico, here we've done it, States, Mexico, Gulf of Mexico, Yucatan, so right there in the sea, and that is where the object hit. So one thing is, like I said in class, we are overdue for a planet extinction event. So if you look at statistics, every 250,000 years, there should be or there used to be a extinction level event on Earth. So we are overdue for one, and that is why we do this research to see how we can protect ourselves. So that, ladies and gentlemen, is this lecture. Do you have any questions? Okay. So like we discussed, we did a poll in yesterday's class. So next week, Monday, is our last class. That class will be online. Then I'll see you for our last class next week. Otherwise, have a wonderful week. I hope you are all voting tomorrow. So please go vote, and good luck with your last week of classes. Yes, I see there is a hand raised. Okay, not anymore it seems. So have a wonderful day, everyone.